All right, so I have a small selection of 62 slides from throughout the quarter that I'm just going to kind of go through. I think like the key slides should get pretty much all the big topics, or definitely all the big topics, and try to hit all of the subtleties as well. But feel free to ask any questions along the way. Like, I'm hoping people will interrupt me with questions. I don't want to go into like specific practice finals and stuff and like practice quizzes and stuff during the actual presentation, just so we don't get too far off track. But I can certainly do stuff on the board and kind of review stuff as we go. And then at the end, with any extra time we have, we can go into specific stuff, like specific practice problems. I also just scheduled my other review session that will be the day before the final, so more of a very last minute thing. I booked Physics 185, where I normally hold my office hours from 12 to 2. I don't know if I'll use the whole thing, but it'll be sometime during then when you can just come and we'll do like practice finals and stuff. But yeah, that'll be super last minute and open to whatever questions you have. And this will be recorded and put up again. Like, obviously you just won't be able to see if I end up doing anything on the board. So I guess without further ado, let's go ahead and go through all of 7B in about 2 hours. So this is where we started. I think this was the first slide of the quarter, but just emphasizing, so we're talking about fluid flow at first, and that's going to be the first question on your final exam. No exponential change, just steady state fluid flow. And when we're talking about flow, we are talking about energy density. So whereas you talked about just energy, like units of joules in 7A, now we're talking about density, which is just energy divided by a volume, or later on we saw it divided by a unit of charge, but it's just energy per something, and that something is whatever is flowing through a circuit. Because the flow is constant, and we just want to track how much energy is flowing through a circuit and how that energy changes forms as it moves throughout. So yeah, energy density. So our starting point for energy density was talking about conservation of current. So again, tracking the stuff that flows through a circuit. In this case, we see a simple pipe where there's two changes, kinetic energy density because the pipe's getting wider, and potential energy because it's going higher up. But regardless of what any of those changes are, whether there's a pump, whether there's a resistance, and it's very important to remember that those things do not change our flow rate, that flow rate or current is conserved in this circuit. So no matter where we are, the amount of fluid measured in volume that's flowing through per unit time is constant everywhere. So I1 equals I2, no matter where your starting point 1 and your starting point 2 is. If you want to think, one way I like to think about tracking flow rate is like fluid passing through like a cross-section of it. If you imagine just like a highlighted cross-section as like a gate, and we're just tracking how much fluid flows through that gate, or like goes through this two-dimensional surface that we just sliced through. So we don't need to work through all the math again of how we got this equation, but current is very simply equal to the cross-sectional area times the speed of the fluid flowing through it. And the units work out. Cross-sectional area is meters squared, and our speed of our fluid flow is meters per second, so we end up with a nice meters cubed per second, or volume per second. And that's true, again, wherever we go throughout the circuit. So now let's talk about the different types of energy, it's all energy, but the different energy density systems that energy can turn into, be spent on at different points in a circuit. So the easiest one, I think, is potential energy density. Familiar form we've seen, it's rho GH. Rho here instead of m being the mass. Rho is just the mass density. So it's mass per unit volume, and that's usually just a number that we're given for water, for oil, or air, or whatever. But the change in energy density comes from the change in h, the height. So the higher up we are, the more potential energy we have. So if fluid's flowing through a circuit and the height increases, like we just saw in the previous slide, the potential energy density will increase. We're going to spend some of that energy density on increasing the height. And one of the most useful things about the potential energy density change, we can exploit it to use standpipes as a pressure gauge. We have indicators for all of the other energy density systems, as we just were seeing here. Height is our indicator for potential. We'll see in a sec that for kinetic energy, we look at cross-sectional area, which tells us about velocity or speed. We can just see whether or not there is a pump or whether or not there is resistance. But pressure, the energy density kind of budget that we have, is harder to track, and there's no just clear indicator for it. We can't feel the force that the pipe has to exert on the fluid or vice versa that would otherwise give us an indicator of pressure. So we use these standpipes where we just kind of pop a straw into the top of whatever fluid we have flowing through. Usually it's open to the atmosphere. And so the water, or whatever fluid, will rise up through it, spending its energy density, spending its pressure on converting into potential. As it grows higher and higher, the potential energy density increases until it becomes the same pressure as the atmosphere. And then we know that the water and the air have the same pressure at that point. So that's why at this top point here, it's labeled PATM. This is another great place or the first great place to mention that we have separate fluid systems here. Even though this is a very simple setup, there's 3 different fluid systems that are present in this example. There's the one obvious fluid flowing from left to right through the pipe on the bottom that's labeled fluid system 1. Then there's the fluid in the standpipe. That's a separate fluid system because it has a different flow rate as the fluid along the bottom. Right? They're both water and they're connected at this point labeled P1, but the flow rate in the standpipe is 0 because it's stationary. Right? If our flow is cross-sectional area times speed, and our speed is 0, flow rate is 0. So we can go back and forth between saying we have a single steady-state fluid system if the flow rate is constant everywhere, or the other way around. If the flow rate is constant everywhere, you have a steady-state fluid system. Here, flow rate's different, so they're 2 separate steady-state fluid systems. And then where the air meets the water at the top of the standpipe, we have another one. The flow rate's the same in that case. There's no flow that we're modeling in the air above, and there's no flow in the standpipe, but they're 2 different fluids, so they have to be separate fluid systems. So with all these fluid systems, the key thing that allows us to connect them is that where 2 fluid systems meet, assuming that meeting point isn't changing, we took a look at that when we looked at exponential change in the context of fluid circuits, but you're not going to see that on the final. You'll only see exponentials in terms of electrical circuits. But anyway, we have a stationary contact point at P1 and at PATM between different fluid systems, and at those points, the separate fluid systems share a pressure. And we know that kind of intuitively because if 2 systems are pushing on each other, pressure we normally talk about as energy density, as energy per unit area, but those units are the same as energy per unit volume, but those units are the same as force per unit area. So maybe that's an easier way to think about why 2 surfaces in contact, if they're stationary, have the same pressure, because they're exerting, now with this new language of Newton's law that we have, equal and opposite forces. And so that stationary point is at static equilibrium. So anyway, they share pressures at the contact points. So if the air is at atmospheric pressure, which we normally model it as, there still would be a change in energy density of the air if you're low or high. However, since the air has such a low density, the rho term is so small, you need a really, really big change in height to notice any significant change in pressure. So for any of the systems we're talking about, we just model the air pressure as constant. So PATM at the top of the fluid column, and then as we go down, we lose potential energy density, and so our pressure goes up. Or if we wanted to explicitly find that from Bernoulli's equation, now we have just 2 terms, pressure, which is always going to be there, or at least you have to start with it and see if it changes, plus our change of potential energy density. Those are our 2 energy density systems. And like I just said, if the height goes up or down, we'll get a change in potential energy density and a corresponding change in pressure. So the way this equation is set up, we have PATM minus P1, so final minus initial, meaning PATM is the final and P1 is the initial. So this Bernoulli equation explicitly right here is applied to this fluid system 2 that's in the standpipe with going from P1 to PATM, so going up the tube. And that's why we have this final minus, or sorry, going down the, going up. PATM minus P1, final minus initial. So this is going up. You would get the same answer, final answer, if you did it the other way around. So if you did P1 minus PATM, but then your delta H term would also have to be flipped. Here it would be 0 minus H, and you'd get negative both of these terms, and so it would give you the same final result. So it's always good if you have a flow, so if I is not 0 when you're setting this up, to go in the direction of flow rate. That way your current is always positive, and it keeps things simple, but the equation works out either way. So anyway, if you have a flow rate, apply the equation in the direction of the flow. Here it doesn't matter, but that allows us to get from PATM to P1, and so we get this nice expression for the pressure at point 1 is just whatever the atmospheric pressure was plus rho GH, so plus some amount, because again, we lowered our potential energy density, and that went back into our pressure. And if we went the other way around from P1 to PATM, it would just be, we would see that PATM is P1 minus something, because as we go up from PATM, we spend some of that energy density on potential energy. So standpipes, you could do this every single time you have a standpipe and do a separate Bernoulli equation for it, going from PATM down to the bottom. And I mean, there's no problem with that. You can see it's a couple lines per standpipe that you have. But as you've seen in a lot of kind of frustrating quiz solutions, sometimes we skip that step and just kind of assume the answer, that our standpipe gives us PATM plus rho GH. And so you'll see cases where there's two standpipes, and so the pressure difference between them is just this like rho G delta H term. And where did it go? Well, it just comes from canceling out the PATM points, and you only end up with the difference between the heights. So that's somewhere that you don't feel obligated to like skip steps like that. But at the end of the day, in reality, like what we're actually doing when we're solving these is using Bernoulli's equation separately for each piece. The standpipe isn't some like freestanding special equation. It's the same exact thing, just applied to a very specific stationary system. Okay, so that's potential energy density. Kinetic energy density, we look for a change in speed of the flow. I'm sorry, I don't know why this text is overlapping here. But as we go from A to B, the thing that tells us what the speed is doing is the cross-sectional area, right? We can't really observe speed unless, I don't know, maybe you like put some dye in the fluid and like timed how long it takes to go. That's a much more difficult and imprecise way to do things. We should just take advantage of this definition of current in our continuity equation, which says that A1 V1 equals A2 V2, or AA VA, whatever. But as the area increases, the speed decreases. And that just comes out of, again, if you think of this like gate system where we're just tracking how much fluid is flowing through each gate at each point in time, if the gate is larger, in other words, the cross-sectional area is larger, you're going to get more fluid flowing through per second, assuming it's all moving at the same rate. Then if you constrict it, to keep that same amount of fluid flowing through, you're going to need to send the fluid through faster, and vice versa. So our indicator for kinetic energy density is area, and as the area increases, the speed goes down. And so in that case, if it's just kinetic energy density and pressure, we'll see if kinetic energy density goes down, pressure has to increase. So potential, kinetic, pressure. We also have thermal energy density or resistance. This one is a bit simpler because we don't have to do any really complex math. It's just the term is equal to minus IR. We could think of it as just delta E thermal over volume as being like another energy density system that we add to. However, you can't get that energy back. Unlike potential, the pipe could just go up and back down, or with kinetic, the pipe can get wider and narrower again. Once you turn pressure into thermal energy, there's no clear way to just turn heat back into pressure within this model. So instead, we'll just take that plus IR on the left and move it over to the right. So we get that the delta P is equal to minus IR. And that way, it kind of makes more intuitive sense, where thermal energy is just dissipation. Whenever we turn pressure or energy density into thermal energy density, it's just a loss, and it never comes back. So in this very simple case, if we just have a pipe moving flat, no change in area, and there is resistance, we'll see that we lose energy density as we go through due to this minus IR term. And since we lost energy density, we lost pressure, the height of the fluid in the standpipe goes down because the height of the fluid in the standpipe is the way we're reading off pressure. We're taking advantage of this pressure gauge. So this is one of those examples where you might see, like if I was writing up the difference in pressure between 0.1 and 0.2, looking at the heights in the standpipe, I might just write rho g H2 minus H1. But really what that is taking one equation that's delta P in one standpipe is PHEM plus rho GH, and then the same one, the other one is PHEM plus rho G, the other H, and then subtracting those two, PHEMs cancel. So if that way still like makes better sense to you and you want to write those out, I think that extra minute or two of working that out is well worth it instead of trying to confuse yourself and maybe getting the wrong sign or something like that. And then finally, we have pumps. So pump is another one. There's not really a complex equation that goes into it. It's just if there is one there, you get a E pump over volume term. So again, sorry, I don't know why the formatting is kind of off in here. But in this case, we're just assuming that we have a pipe, and the only thing there is a pump. And so our delta P going from one side to the other in the direction of the flow, assuming the pump is oriented that way, we'll just get an addition of energy density. Yeah? Because there is resistance. So it's dissipating some of that pressure, spending some of that energy density on resistance. Whereas the pump is just adding. So that you can think of thermal energy density or resistance and energy from the pump as being like the things that change our balance. The pressure, kinetic, and potential, those all go back and forth throughout a circuit. And then if you want to maybe think of it in terms like net force and like what's our system, like that type of method of thinking, the pumps and resistance, those are like the net, the external things that are acting on the system that add energy and take away. And without those, we're constrained to just juggle around the same amount of energy in between pressure, kinetic, and potential. So putting that all together, we get our complete Bernoulli equation, which looks like a lot, but the nice part is it really describes a whole lot of behavior. So this whole unit is based off of this equation, in addition to current, just like A1, if you know this equation, or not know it because it's on your equation sheet, but know how to use this equation and also know A1 V1 equals A2 V2, that's really all of fluids. And the intricacy just comes into applying it, which again, it's important to define your system. So which steady state fluid system are you looking at? Making sure that it is indeed just one steady state fluid system. What's your starting point and what's your ending point? And then from there, I guess it's just kind of plug and chug. So yeah, it demonstrates energy density conservation as we flow through the circuit. Everything is an energy density, and of course, these are changes in position. Yeah. Good question. So it really seems like it could, and that's kind of one of the places where at least my intuition turns me wrong. Is like you see a pump and you think like, oh, that's going to speed up the fluid, right? You think of it, it's like kind of, if I'm a water molecule flowing through a pump, it's going to like shoot me out the other side, which seems like it makes sense, but it's not true. The pump does not affect the flow rate. So you could put as many pumps as strong as you want in, and your flow rate will not change. Well, that's not quite true. So when I say put in a pump, that means I might change the system. So if I have one, let's say, I have this system here. There's no pump, and this is a given flow rate. But then let's say I take this pipe and add a pump to it. The flow rate of the system with and without the pump does not have to be the same because I changed the system. I added a pump. So that could be somewhere where you might see in a problem where if you make an alteration, if you want to make an altercation, that's fine too. But if you make an alteration to the circuit or fluid system, whatever, then then you're going to have to solve for a new current. But the flow rate from one side of the pump to the other is the same, and thus the speed is the same. Okay. That's, yeah. Yeah, so pumps do change, well, they change the energy density. So if you only had a pump, then yeah, it would just be delta P equals E pump over volume, and that energy density would go directly into it. So if you just had a pipe with no resistance, no change in height or change in area, then on one side of the pump, you'd have a lower pressure, and on the far side of the pump, you'd have a higher pressure. And that would be the difference, not the speed of the flow. Just it would be moving at the same speed, same flow rate, just higher pressure, meaning each molecule has more energy density. You could have a pump oriented like the wrong way. For instance, like when we saw, this is skipping ahead a little bit, but like thinking about batteries, which act as like our pump in an electrical circuit, you saw a problem where two batteries were oriented opposite each other. And so the current is going to flow the way that the stronger battery wants it to. And in that case, the weaker battery acts as like a pump oriented in the wrong direction. So in that case, it would just be a negative change. So that's something that could technically happen, but it would be like very explicit in a problem if a pump was not oriented the way that we're used to. Yeah, so changing the density of fluid, I don't know if I could give an overall rule, whether it like increases or decreases, but the terms that it could change are, well, I think potential energy density and kinetic, because changing a fluid, what it does change is rho, is the density. All the other things like the speed, the cross-sectional area, all of that other stuff is either just like a given or comes out of the math. But the physical property that changes is rho. And that term, like rho gh, it appears in potential. 1/2 rho delta v squared, it appears in kinetic, but none of the other ones. So those are the terms you'd have to take a look at. And then the math could work out either way. Maybe the changing from water to oil makes the pressure go up or down or whatever. Any other questions on fluids? The next slide is circuits. So, yeah.
So on one of the exams, I had a couple trying to figure out the problem with fluid flow. Do you have any tips on how to solve the puzzle quickly in a math problem like this?
Yeah. So the question is really just kind of general problem-solving advice on these. And I will say that I think these are the hardest problems to solve on an exam because the setup is a little more convoluted. Everything else in this class is more or less just a collection of lines at different angles. And so the geometry is hopefully a little more clear. But here it's a little more free-form. None of us are artists. Our diagrams tend to be a little wonky. So I think the best recommendation I have for solving the puzzle of these is to take a second before you could write this equation down, but before you start trying to plug anything in, just try to identify really where those indicators change. I guess even before that, again, identify your system. So make sure, even draw for yourself the line of flow that you're looking at. Ask how many fluid systems do I have here? Most of them are bound to be either uninteresting or things that you can kind of skip a little bit, like the standpipe type thing. But when you identify your main line of fluid flow, and then once you have that, just where is H changing? Where is the cross-sectional area changing? Doing those little things and just kind of recognizing where the important parts of the problem are before you start plugging in are good. I don't want to discount that first step of deciding what your system is, or what 2 points you're finding the change between, because a lot of quiz problems or final exam problems have a situation where you're only looking, or it makes more sense to only look at one section of it. So you might have a whole complicated mess going on, but then there's just there's just a difference between two standpipes somewhere else in the circuit. And if you have some information that lets you just get between those two, it might be completely irrelevant what happens elsewhere. It's hard to say without an example in front, but this one, it really, really pays off to do some thinking before you start trying to write things down. All right, So electrical circuits. So this works super similarly. Remember, it's not going to be on your final, but after this we just generalized even more to how general linear transport systems work, or models work. But this one is super similar, where we have an energy density, except now, instead of being carried by volume of fluid, so like every cubic centimeter of water has this much energy, which is what pressure is, now we have voltage, which is just saying every unit of charge has this much energy. And instead of water molecules flowing around, it is units of positive charge. And so diagram-wise, we're usually going to have a battery, at least without the presence of a capacitor, but the battery acts as our pump. And so it's a good starting point in our circuit. So we know the battery sets up this voltage difference, just like a pump. On the negative side, we'll have a lower voltage, and on the positive side, we will have a higher voltage, and that voltage difference will usually be given as just like this is the voltage of the battery, just like this is the energy density of the pump. And the rest of our job is really just to track how that energy density changes throughout the rest of the circuit. Except with electrical circuits, the trick isn't so much having a bunch of different energy density systems that it changes between, it's just the setup is more complicated. In that we'll have resistors branching off and being in parallel and series, which we'll talk about in a sec. But the overall, like the foundation, the building blocks of the electrical circuits are basically just the right side of the Bernoulli equation, this E pump and minus IR, or in this case, your epsilon for the battery and minus IR, except we'll have a lot more of those and have to see how they add together. And then on the left, we only have our delta V, our change in voltage, which works as our pressure term. That's our budget to either gain, we get deposits from batteries, or expenditures on thermal energy dissipation in resistors. Our units of current here are charge per time, coulombs per second, which we call amps, but that's the same thing as our current before, where it's this conserved quantity that flows through, and it will be the same at every point we'll see when things branch off, but we still do have a conservation of current. We'll just have to pay a little more attention to that. And this, you won't need to ever talk about the flow of electrons specifically on the final, but as we all know, electrons are what flow through wires and circuits and stuff, but for some reason in physics, we model it as the positive charges that are moving, which it's not physical, but the math does work out so that our current ends up being positive. And I guess it's just kind of more intuitive to think that current flows from positive to negative, like from high voltage to low. Okay, so a little more on voltage. Like we said, the units are energy per charge, so joules per coulomb instead of unit volume. That's the energy density that we have to spend throughout the circuit. Again, the delta here we're talking about is spatial, so we're just finding the change in voltage generally between different points in the circuit. So depending on the problem, deciding what those 2 points are is really key in getting the answer, because there will be a lot of circuits where there's a million different deltas that you can find, and while you may be able to solve for many of them, oftentimes there's easier and more difficult choices that you can make to get toward your answer. So maybe we'll see some examples of that. The elements of the circuit, I already said some of this stuff, but we have the battery, and the delta V across the battery is epsilon, so that's just the difference in voltage across it. If this is a 3-volt battery, on the left of it, before the negative end, we could be at 0 volts, and then once we go through the battery, we'll have +3. So the battery just injected this energy density, gave it to each joule. Each coulomb of charge now has 3 joules, whatever, of energy to spend throughout the circuit, and it will. And that brings us to our loop rule, where when we travel in a whole loop throughout a circuit, we have to get back to the same energy density that we started with, or the change going from one point all the way around needs to be 0. So whatever combination of batteries and resistors we have, increase in voltage due to batteries, decrease due to resistors, that all will work out to end up giving you conservation or satisfying the loop rule. And the way that works is that current changes, right? Or current kind of responds to that. You have whatever collection of batteries and resistors, you put them together in whatever configuration, and the current that results will be the one unique current that satisfies this loop rule. And that's kind of the basis of this whole unit, is figuring out what that, it might not always be the current that we're after, but physically that's the important part, is that the current obeys this. That's how the circuit knows what current to send through, or how excited these electrons should be. So in a very simple circuit, when we just have a battery and a resistor, we can use our loop rule. Let's say start at point 4, go through the battery, we get epsilon, go through this wire, which we model wires as having no resistance, so there's no change in voltage between 1 and 2, but then going from 2 to 3, we have this resistor, and so we have a delta V, or V23, or like V3 minus 2, but this is just the delta V as we go from here to here, and V final minus initial will be minus IR. We dissipated some of that energy that the battery gave us. And in this case, since it's all that the current has to pass through, right? Once it goes through this resistor, there's no other elements, so we get right back to where we started. Because this is the only other circuit element that the current sees, all of the energy density, whatever that may be, 3 volts, all of that 3 volts will be dissipated here. And that comes out of our loop rule. If epsilon is 3 volts, and 0 equals 3 volts minus IR, then minus IR has to equal minus 3 volts. And so we can plug things in here and solve for the current. And this is, again, the most simple electric circuit we could have. Things get more complicated when we have multiple resistors, which we pretty much always do. Series resistors are just when we have one after another, and we're not going to derive these equations again, which we could. These were derived just by using the loop rule and conservation of current. So they're not just like magical relationships. They're a must in order to obey these very simple principles that we're starting with. But when resistors are in series, or one after the other, meaning, and another like technical way to say it is that resistors are in series when they share the exact same current. So even if you can trace a line from one to another, if the current has a chance to split off, in other words, some of the current that went through the first one doesn't go through the second one, then they're not in series. But in this case, you can see all the current that goes through R1 has to also go through R2, and so I1 has to equal I2, which in this case also equals the total current. There's just one value. But anyway, we find out that the resistances just add. So when they're sequential, when they're in series, one after the other, we just add the resistances together. And again, the currents are equal for resistors in series, and that's another one of these things that goes both ways. If the currents are equal, you know they're in series, or if you know they're in series, then the currents are equal. But the voltage drops do not have to be, right? We're going to get some minus IR for R1, so minus IR1, and the same minus IR, not the same, but same form, minus IR2. But R1 and R2 don't have to be the same, right? If R1 is much bigger than R2, then minus IR1 is going to be much bigger than minus IR2. And so that difference in voltage drop between them just depends on how big the resistors are. Yeah.
I have a question on the last slide.
Mm-hmm.
If there's no current flowing through the circuit, the voltage drop for the resistor would be R, but the battery would still have a voltage drop, right? But that doesn't make sense. Since they're in parallel, they would have the same voltage drop.
Yeah, so saying that the battery and the resistor are in parallel, in a way that's true. That's maybe a more difficult way of thinking about it, but the setup is not possible. So in this case, if you had a battery with some voltage and it was connected to this resistor, the current could not be 0. Like you just described, it doesn't make sense. It can't obey the loop rule. And that's because like the loop rule, if you apply it, will give you the current. So that current can't just be whatever we pick it to be. It's determined by what's the voltage of the battery and what's the resistance of the resistor. And then that is what the current's going to be. Yeah. Okay, so we went over series resistors, one after the other, share a current, not necessarily a voltage drop. The more tricky arrangement is when they are in parallel, and that's when the current can go through either or resistor. So we find here that the currents are not equal, but instead the currents add to whatever the total current was, or the total current that was going into them. So whenever you have resistors that the current can go either or, you're going to have a junction. Like we see here, the junction is this point when it first splits off, when, in this case, 3 different wires meet together. It's not always a point, which we'll see sometimes that gets tricky, but the current is no longer the same everywhere in the circuit. If we just think about it in like very small, unrealistic numbers, let's say I have 4 electric charges, that's my I total, so 4 electric charges per second coming through out of the battery. Then when it hits this split, I certainly am not going to have 4 go each way per second, because then I have 8 per second. I just can't create these 4 electric charges out of nowhere. So whatever the amount of charge going through has to be conserved. So I still only have 4 to work with. It might be 3 and 1, or 1 and 3, or 2 and 2, or whatever. That will have to do more work. But we find that the sum of the currents of all these parallel branches, and it could be more than 2, equal our total current. And that, combined with the loop rule, we find that the resistances obey this equation here. It's kind of like the one for series, except everything is 1 over itself. So each term is the inverse of what it would be. So yeah, be very careful when you're applying this one. We all do it from time to time, but it's very easy to just do REQ equals 1 over R1 plus 1 over R2 and forget to put 1 over REQ and flip that final one. So that's just another defense of keep units in your work, because it helps, you'll end up with a result of 1 over ohms, which doesn't make sense. But yeah, so this equation is important, and when we solve it, we get an equivalent resistance. So I kind of just brushed over what an equivalent resistance was with series. I just said the resistances add. But really what we're searching for is a single resistor that we can replace a bunch of resistors with. Why? Because, well, it's much easier, and it allows us to solve that simple loop rule of epsilon minus IR equals 0. Except if we want that single R, we have to obey these rules for simplifying it. So if I took out this R1 and R2, just leaving now 2 ends of wire, and replaced it with a single branch, a single resistor, that resistor would have to have REQ. Another way of saying that is it's whatever resistor we replace the branches with, or the series resistors with, that gives us the same current. So that's going back to why current is what it is in a circuit. The current is just a product of what the voltage of the battery is and what the resistance it sees is. So if you think if you're the battery and you're giving energy to these charges, you don't know, all you know is the wires on either side of you, and you know what the voltage drop needs to be, whatever the voltage of the battery is. The battery can't tell whether it's hooked up to 100 resistors that have an REQ of 2 ohms, or a single resistor that itself has a resistance of 2 ohms. It just knows that the total resistance, or the equivalent resistance of what it sees, is that 2 ohms. So that's the whole goal with replacing it, all the resistors with REQ. Yeah. Good question. Yeah, I'll do that in a couple slides. So there's a couple rules that kind of guide us. But yeah, the question was, how do we know what the order of operations when we simplify? So I'll go over that soon. So anyway, takeaways from parallel resistors, we have this equation for the equivalent resistance, and again, we know the currents are not equal, but that they add to the total current going into the branches, but the voltage drops are equal. And that key fact that the voltage drops have to be equal comes from looking at the loop rule. If we look at this circuit, and first we track through the battery, and then through R1 and back, that's a loop. So it obeys the loop rule that the total change in voltage has to be 0 as we go through. And we have the same loop rule through the bottom, going through the battery, and then going through R2, and going back. So whatever the voltage drop of the battery is, no matter which resistor I go through, I have to lose whatever the voltage the battery gave me. And so the voltage drops have to be the same. as a result of the loop rule. All right. And so yeah, that is very frequently the key to solving one of these problems, is just remembering this fact. And it can often save a little bit of work because this comes out of other equations like finding REQ and, I don't know, working through a whole set of things, but very often you can use just the fact that in parallel branches the voltage drop is equal to solve problems. I'm going to come back to power because I want to do the simplifying circuits thing first, and then we'll go back to that. So this goes back to the question of how do we know what order to simplify circuits. The ones I've shown so far, and even this one really, are pretty simple. And by simple, I mean that they're drawn in a way that makes it more obvious. They're not drawn in a way to trick you. But still, here there's a lot of choices seems like I could make if I wanted to simplify this into a single REQ. Right? I have 5 resistors. Clearly, there's some combination between series and parallel. And so I just see this, and I'm kind of immediately stuck in how do I go about using those two equations and combining series and parallel. And I think the keys to it are that you can't combine resistors in series through a junction. So for instance, R1 and R2, right? I can trace my finger going from R1 and through R2. So why can't I say those two are in series and first simplify R1 and R2 into a single resistor that has resistance R1, 2? Well, because I crossed a junction, right here. And when I cross this junction, in other words, like past a point where the current can go elsewhere, this tells me that R1 and R2 do not have the same current. And the whole way we found out that equation for REQ for series resistors, that like REQ is just R1 plus R2 plus R3, whatever, we found that by assuming that they had the same current. And so here they don't have the same current and we can't combine them yet. So that's how you know when you can't combine them in series, is that you can't cross a junction. So that crosses off a bunch of other choices. I also can't combine R1 and R4 for the same reason, or R1 and R3. I can't combine R3 and R5 because, again, crossing a junction. Here, instead of current splitting off, it joins us again. So the current through R5 is going to be greater than the current of R3, but it doesn't matter. They're not the same. And visually, it just means, again, you can't cross one of these points where you have more than 2 wires connected. For parallel, you can't combine things in parallel unless you have a single resistance on each branch. So what if I just wanted to go right ahead and connect R4 and R3? Well, R3 has R2 in that branch. So maybe a clearer way of saying this, and in the same vein as what I said about series, is that the thing we know about resistors in parallel is that they share a voltage drop, right? For series, they share a current. In parallel, they share a voltage drop. Here, R4 and R3, or R4 and R2, do not share a voltage drop, right? It looks like they might be in series because they're in different branches that are alternates of one another. But the voltage drop across R4 is equal to the sum of the voltage drop across R2 and R3, right? We know that the voltage drop going from this junction on the right, where the current first splits off, to the voltage that comes out of the junction, where it comes back together, that's what our reference is. That's what the voltage drop across both branches has to be. And so, yeah, I mean, maybe the simplest way is what I said originally, is that when you're combining things in parallel, you want to make sure that there's only one resistor in each branch, but really what we're saying is that you can only combine things in parallel that have that equivalent voltage drop across them. So now let's apply these rules to this circuit. I've said why I can't combine things like R1 and R2 or R4 and R5. I can't combine those in series because it crosses a junction. I can't combine R4 and R2 because they don't share a voltage drop, or in other words, this branch has 2 resistors and this one only has 1, so I would need to simplify that. And so it's kind of a process of elimination here, that the only thing I can combine are these 2 in series to start with. Right? These 2 going from R2 to R3, there's no other place to go, and so all the current that goes through R2 has to go through R3. So I'm going to start by combining those 2 in series to get R23, and to do that, we just add their resistances together. And so we get 7.5 volts from the sum of 5 and 2.5. Now, I can do that same process of elimination. I cannot combine any of these in series. I can't go from one resistor to any other resistor without crossing a junction. Well, actually, I guess I could combine 5 and 1, even though they're on opposite sides of the battery. I could do that if I wanted to, but I don't know, that's maybe less clear. But now, R4 and R23, those are in parallel, right? I can either go through R4 or R23, and there's only one resistor in each one of these branches. So that's a prime candidate, and so why don't I go ahead and do that? And so if I use that 1 over REQ equals 1 over R4 plus 1 over R23, I get that R234, or the equivalent resistance of these two connected in parallel, is 3 ohms. And this brings me to a good place to recall this little trick, or just like more of a check on our work. When we combine resistors in parallel, the resulting REQ is always going to be smaller than the smallest resistor in parallel. Right, so the two we had in parallel here are 5 ohms and 7.5, and so we know that whatever the REQ of those two branches is going to be smaller than 5 ohms, which it is. It ends up being 3 ohms. And the intuition behind that is, well, think about any individual resistor hooked up in a circuit. It's so difficult for current to pass through it, and then no matter what that other resistor is, if I add another resistor as another option, that lightens the load of that first resistor that I had. So again, independent of whatever the values of those two resistors are, I'm just diversifying, giving the current more places to go, and so spreading it out, making it easier for it to go through. And so even if only by a little, it will make the equivalent resistance smaller. Yeah. Yes. Yeah, so that's why you could technically combine R1 and R5 in series, and that's fine. It's kind of weird because there is a battery in between, but it's totally valid, yeah.
What if you had an additional resistor instead of a parallel circuit? Then how would the current?
In that case, the equations, so I haven't shown it here, but those equations, that the 2 for REQ, depending on series or parallel, work for as many as you have. So if they're in series, just keep on adding them up, and if they're in parallel, you just 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth. And the same rule would apply. If I had a third branch here, if it had a single resistor in it, then once I combine these two, then I can combine those 3 together. But if it had 2 or 3 or 4, I would need to turn those into a single resistance before I can combine these all in parallel. Okay, so now we're just left with 3 resistors in series, and so I can add them all up, and I get my final equivalent resistance of the whole circuit. And this probably wouldn't be our stopping point. Now that we've done all this work to simplify, then we expand again, except with more information. Getting to this point, again, the key of this was that it allowed us to know what our total current is, or what resistance did the battery see. And so how much charge per second, or how much energy, or how much charge per second is going to come out of the battery, right? That's what current is. The greater this resistance is, the less charge per second is going to flow through. And so now we determined what these two are. I don't have the slide with all the math in here going backwards, but we get a total current. And so that would tell me, and whatever that total current means, would be that current going through this REQ would give me a voltage drop equal and opposite to that of the battery, right? You'd get plus 19 volts, minus 19 volts, plus 19 volts, minus 19 volts, obeying the loop rule. If I took a step back, now all of these resistors still get that same current, right? They're all in series. There's nowhere for it to go. So I would get minus R1 times I total, minus R234 times I total, minus R5 times I total, and I would get the same total voltage drop as I would for just REQ. Going a step even further back, now the interesting part, I have these 2 parallel branches. So now I have a place where I'm not going to have I total, right? I total is going to split, and some of it's going to go to R23, and some of it is going to go to R4. And how are we going to determine how much goes to each branch? Well, from that key point, which I said was that the voltage drop across parallel branches is equal. So I know that whatever voltage drop across R4 I have is the same as R23. And even more crucial, or equally crucial, they're all crucial, the voltage drop across R4 and across R23 is going to be equal to the voltage drop across their equivalent resistor. Because when you think about what resistors in parallel are doing, they're all providing a different way to get from one initial voltage to one final voltage. All the different paths give you the same change. And so the resistor that we put in place to replace all of those branches needs to do the same thing. It needs to get me from that same starting point to the same final. So delta V234 is the same as delta V4, and it's the same as delta V23. I total goes through R23, and I total splits up into these two, but those voltage drops, all three of them, are equal. So with the voltage drop that I found in the previous slide, when I just did I total minus I total times R234, I can apply that voltage drop and say that's equal to R4 times whatever current goes through R4. And that's also equal to R23 times whatever current goes to R23. And so I know this is a lot to say without writing stuff out, but what I'll find is that because they have the same voltage drop, the one with the higher resistance is going to have a smaller current, right? If IR is equal to, like IR1 is equal to IR2, or really I1, R1, or I23, R23 is equal to I4, R4, then if I23 is bigger, then that means R23 is smaller. It's not here. But anyway, the intuitive part of that is that more current wants to go through the easier path, right? The easier path being the one with lower resistance. And so we'll find that R4 is going to get more of that I total than R23. It's still going to be less than I total, right? They have to sum toward I total, but more of it's going to go the easier path. And that's true always. And if we have lots of branches, the smallest resistance branch is going to get the most current, and the highest resistance branch is going to get the least. So simplifying circuits, I don't have examples in this slideshow, but things to look out for when you're studying for yourself. I would really focus on doing practice problems where they're drawn in a tricky way, like the butterfly shape where you see parallel branches that instead of just drawn like a ladder, like you see here, where it's just like, one on top of the other, maybe the battery's in the middle and it can branch out, or you get junctions of multiple resistors that look like, I'm sorry for the people that are watching this on the recording, but you might get something like this, where here's two resistors that are clearly in parallel, right? We know how to deal with that. But then you might have something like this, a third one that's drawn where the junction is at a different point than these two. And it looks like we should treat this top resistor differently, right? Because it's connected in a different way. But at the end of the day, the voltage here is the same as the voltage here, is the same as the voltage here and here, right? Even though this junction occurred here, the current might be a little different. The important stuff happens at the resistor. And so all three of these resistors all give us a way to get from my starting point to my ending point. And they're all going to have the same voltage drop across them, and thus all three of these are in parallel. This top one could also easily, like in a more easier fashion or clearer fashion, be drawn like that, in which case maybe we would more immediately recognize that they're all in parallel. But that's what I mean. For when you practice stuff, gravitate toward ones and like redo them without looking at the solutions, just simplifying them. And maybe don't even take the problem to the end, but just do the important part of figuring out what REQ is when the circuit is drawn in this like tricky manner. All right, so questions on circuits without capacitors. So I'm about to move on to capacitors. Okay, so before we explicitly bring in capacitors, let's just talk about exponential decay, just from like a math perspective. So this is the general equation for a decaying exponential and the corresponding graph, but we get y of t, like some value y that's varying with time, is equal to y naught, whatever its initial value is, times e to the negative t over tau. So let's break it by plugging in values of time, right? So this is an equation. If I plug in a value of time, I get a value of y. So if I put equals 0, in other words, y of 0, e to the negative 0 over tau, or just e to the 0, is 1. And so my result is just y naught. That's why we call that constant y naught. You could easily call it like a, b, or whatever. It's just a constant that tells you the height of the original graph when it starts to decay, but we call it y naught because physically it means our starting point for our decay. So we'll put that on the graph. At t equals 0, we start at y naught. If I plug in a little bit later of a time, tau, so we haven't talked about what tau is yet, but it's the time constant, we all know, but it's just some value of time. The units of tau are time, so if we plug in t equals tau, I get y naught times e to the negative tau over tau, or e to the negative 1, which is 1 over e. And so y of tau is equal to our original y naught, at time equals 0, over e, which works out to about a third. So what that's telling us about this value tau, and also about the shape of the function, is that after tau amount of time, after the time constant has elapsed, we've decayed to about a third, or really 1 over e, of our initial value. So it's a quick initial drop. Exponential decay has quick change in the beginning. And then if we plug in a really huge time, so like t is much, much greater than tau, we get y naught times e to the negative really big number. And e to the negative really big number is essentially 0. And that's why we get this asymptotic movement towards 0. But keys here are that, well, we have decay, and that the decay is getting slower over time. And so really, I mean, in this case, the value of y is decaying, right? We're starting at y naught, and we're going toward 0, right? So that y is decaying. But really, specifically, what we're talking about with exponential decay is that the slope, the rate of change, is decaying. And we will talk specifically about what rate of change is, but just from in a more plain English perspective, it's saying that over time, my system is stopping, it's reaching an equilibrium, right? It's rapidly changing, and then the speed at which it's changing is slowing down as it gets closer and closer to its equilibrium value, right? The distance from equilibrium is what causes the system to move toward it, right? The system wants to be in equilibrium, so if we put it really far from that equilibrium, it's going to shoot toward it. But then as it gets closer and closer, it becomes less dire because we're not as far from equilibrium. The system's less unhappy, if you will, and so it slows down. And that's what's happening here. When we first start, and this is still just kind of general, but whatever the system is, we start with our initial value of y naught, which is far from equilibrium, and we rocket toward equilibrium, but then as we approach it, we get slower and slower and slower. And what we mean mathematically by slower is the rate of change, the slope, the rise over run, or in this case, the drop over run. But we change in a small amount of, early on, in a very small amount of time, we get a large change in y, but after some time passes, we can have a really large change in time and a minimal change in the value of y. So this shape is really indicative of what exponential change is. And it's also important to note that this is asymptotic. So not at y naught. The initial value is not infinite, right? And that's something we often mistake too, is drawing two asymptotes, which isn't true. There's only one. We start at some finite value, y naught, right? That's just a measurable where our system starts. And then the infinite part is the amount of time it takes to actually reach 0. It just gets infinitely closer. So that is kind of an artifact of our model. No, systems don't actually take an infinite amount of time to decay. If we're talking about charge, for instance, there will be a point when the last charge hops across, and then we'll get 0. But this model is very, very, very good from a macroscopic perspective. Okay, so this is what exponential decay is. We're talking about the rate of change of y depends on the value of y itself, right? The smaller y is, the smaller the rate of change. And we're talking magnitudes here. It might even, the rate of change is negative, right? So when we say it's becoming smaller, it's actually becoming more positive. In other words, we have a very negative slope here, and then it becomes less and less negative. So in a way, it's increasing, but the magnitude is decreasing. The steepness is what's decreasing. So the time constant acts as this kind of breaking point. It's not like nothing physically happens after one time constant has elapsed. It's not, like physically special in that sense, but it does give us like a rough characteristic time scale of our system. Like we can see on the graph, before one time constant has elapsed is roughly this area of steep slope and rapid change, and afterwards is when it really starts to noticeably get more shallow and go to this slower changing amount of time. And just from a value perspective, again, it's when we've hopped from our initial value down to a third of our initial value. And so it just gives us a good scale. If your time constant is on the order of a few seconds, then after a few tens of seconds, your system's going to be at equilibrium. If your time constant is on the scale of hours, however, in a few seconds or a few tens of seconds, there's going to be very little change at all. You'll have to wait tens of hours in order to really get to this amount of time. So the time constant is useful for categorizing and, of course, mathematically working with a circuit. So this time constant comes from the physical quantities involved in the system. Depending on what it is, like if it was fluids, it would be like resistance, gravity, density, stuff like that. But since we're only talking about capacitors, it just depends on the resistances and the capacitances in the circuit, which we'll talk about soon. Okay. So yeah, it's kind of stuff I've already been over, but the slope starts to become shallower as time increases. Another thing I want to say about the time constant is, and we don't touch on this much, but the behavior of exponential decay systems is, I don't want to say constant in time, because it's not really what's happening, but you could start at any point. So we normally just talk about starting like when the capacitor has no charge on it, and then seeing as it charges up to being fully charged. Or the capacitor is fully charged, and now it's going to discharge across a resistor. And so we haven't had to think about this much, but what behavior occurs when we start with the capacitor halfway charged, let's say, and then see it charging from halfway to fully charged, or the opposite, where it's like halfway discharged, and then we're seeing how it proceeds all the way to zero. This exponential behavior occurs no matter what. So the same amount of time, another way of saying that, the same amount of time it takes me to go from my initial value to 1 over e, or like roughly 1/3. So this first time constant, after another time constant, I'll get to 1/3 of the value, or like 1 over e, of the value that I was after a single time constant. And so on. So after each time constant, I get that decrease to 1/3 and 1/3. And that just compounds really quickly to 0. Yeah. Exactly. So no matter where I start, after one time constant, I'll be exactly 1 over e lower than where I started. Maybe it's easier to think about it in terms of half-life. So you'll get just the equation for converting time constant to half-life on the formula sheet. You don't have to memorize it, but half-life is an easier thing for us to think about because a half is easier to take than 1 over e. But it's just more of a matter of convenience. A half-life is a similar thing where it's just telling us how long it takes to get from my starting value, except to instead of 1 over e to 1 over 2 of my initial value. It just happens to be uglier math to find the half-life. But anyway, let's say my half-life is 2 seconds, and I start with a capacitor, which we'll talk more in detail about soon, but a capacitor that is charged up to 10 volts and is discharging. After one half-life, or after 2 seconds, it will be at 5 volts, right? That's what a half-life is. And then after another 2 seconds, it'll be at 2.5 volts, half of 5. After another 2 seconds from there, it'll be at 1.25, and then 0.62, whatever. So it just keeps dividing by 2. And so this exponential behavior, if I zoom in on any point of this curve, it will look the same, which is kind of cool. So anyway, I don't want to say outside of the scope. But I think the intuition for this stuff is important to help you think about these problems on the final, even if I'm not going to give you a question that says, explain the intricacies of, the scale behavior of exponent. It's just, so you know what you're looking at. Okay, so now let's connect this actually to capacitors, which I kind of did a little bit, but explicitly just backing up what are capacitors and how do they work. So at the end of the day, and now this slide I think is clearer now that we've seen this through once around, but a capacitor is just two conducting plates in a circuit. We're snipping the circuit where we normally just have two ends of wires, and so where no current can flow because there's nowhere to draw current from, right? We just have like an empty wire. And now we're making them two big conducting plates with tons of charge on them. There's not a net charge on either of the plates, right? So there's an equal amount of positive and negative charges on each, but there is charge to draw from. And what happens when we have a capacitor that's working in a circuit and moving toward equilibrium is that charges are being passed back and forth. The battery is pumping charge from one side to another. So in a case of this like this one I have up here, I have an uncharged capacitor, meaning these two plates are, again, net zero charge, same amount of positive and negative, and I plop a battery on there, and what the battery does is set up this potential difference, right? When I put the battery here, now the left side has a higher voltage than the right. And the charge responds to that, right? The charge wants to be, is like going to respond to that. It's going to be pumped by that charge differential. And so, this will maybe make more sense when we look at it in the context of a loop rule. But what happens is the positive charges get pumped over to one side, leaving an excess of negative charge on the other, and the capacitor pumps up. So why does this stop? Or why does this behavior, why is there an equilibrium? Why doesn't this just happen forever? Well, charges don't like to be in the company of their neighbors. They're contrarian. The positive charges don't want to be near positive charges, and the negatives don't want to be near negatives. So the more I pump from one side to the other, and the more I surround these charges by their peers, the more they're going to repel, and the harder it's going to be for the battery to pump more charge from one side to the other. So that's why we get this exponential decay behavior, where initially it's free for the battery to pump charge from one side to the other. It has this energy density to give out, and so it just sends charges across willy-nilly. But then as they build up, it has to fight against that, and so it slows down as it reaches equilibrium because there's something pushing against the battery. So the math behind this, how do we connect this repulsion force to a voltage change, is this with these equations here. So thinking about it in terms of voltage change, I write delta VQ here because it's a voltage difference due to this difference in charge, but you'll often see this as delta VC. It's just the change in voltage across a capacitor. And it's a function of, as we expect, the amount of charge on it, Q. So the larger Q, the more charge I pump onto a capacitor, the larger voltage drop, meaning the larger energy density it takes to sustain that. And then the other component to the equation is C, the capacitance, which just has to do with the physical properties of that capacitor. If we think about some basic physical characteristics, if you just take two of the same plates and make them bigger, if I have more metal plate, that means more charge to pull from, more space for these charges to spread out. It becomes easier to move charge across. So if I increase capacitance, in other words, make it easier to put charge on the plates, then the voltage drop is smaller because it doesn't require as much energy density to sustain that. The charges are less eager to leave the plate. So more charge, higher voltage difference, higher capacitance, lower voltage difference. And we can rearrange this equation too to solve for the amount of charge on a capacitor. If we think of delta V here as the voltage difference applied to a capacitor, so in equilibrium, maybe that is just epsilon of the battery. If I have a larger battery connected and apply a larger delta V between the two plates, I'll get more charge built up. And if I increase the capacitance with the same amount of voltage, so if I make it easier to put charge on there, the same battery can pump more charge onto each plate. And so these two equations just work together, but this delta VQ or delta VC on the right, this is the term in the loop rule that we're going to use because it tells us when we're applying our loop rule how to account for this circuit element that is a capacitor. How does my voltage change when I'm tracing from one side to the other? Yeah. Yeah, so the C is not the units of capacitance. It's the variable for capacitance. The units are farads. We'll normally see F for that. Yeah, and we don't go into it too much. I kind of contradict myself here when I stress the importance of units, but For our purposes, I think units are important. The pros for units are that they can be helpful when you're solving stuff, because if you get the wrong units, it leads you to figure out that you did something wrong with the algebra. That's good. Also, you probably run into a ton of units on like MCATs and whatever, like in biology and whatever. Units are really important. Against them, though, it's like, seems kind of not arbitrary, but I don't know. I don't want to take points off because you wrote like C for units of capacitance or something like that. So, and the units of capacitance in ohms aren't really intuitive anyway. So when it comes to farads and stuff like that in electrical circuits, very often we'll just write something out and know that this expression is one that gives me a voltage change, and so I'm just going to write down the numbers in units and slap volts on it at the end, because that's what I know they do. But if you really want to work it all out, you can see that these units all have fundamental base units in terms of charge, seconds, and meters. Yes. So yeah, a larger capacitance means it's just easier to push charge across. So yeah, if it's easier, you'll get more charge to build up. And then yeah, if you have a fixed amount of charge, if you increase the capacitance, then that charge can spread out more, and so the voltage difference is going to be smaller. Okay, so finally, let's put this in the context of a loop rule. Again, we take the capacitor plates and just put them next to each other. A, because it visually makes our circuit look like a circuit, but B, because this actually increases the capacitance of a capacitor. That's why when you use capacitors in a lab, they're not these big things with plates spread out. They're next to each other because the amount of attraction that occurs between the two plates does increase the capacitance. Right? Now these negative charges don't want to be near negatives and positives don't want to be near positives, but we sweeten the deal a little bit by putting the opposite charge across it. So there is physical significance to that. But it also sees that now a capacitor is a functioning element in our circuit that we can evaluate a voltage change for, just like any other element. Right? So now we go through the battery, we pick up this epsilon, then we come down to our capacitor. And now this is a point of very frequent confusion, understandably, because there's positives, there's negatives here, there's like this delta V, Q, VC thing. How, like, is this a positive voltage change? Is this a negative voltage change? An overall rule that might make it easier is just like when you're charging up a capacitor with a battery, the voltage drop across the capacitor is negative, right? And that's in this context where we have the battery, and then we go through the capacitor, and we get a voltage drop, go through the resistor, get a voltage drop, and come back to zero. So just like kind of, it works in our flow of the loop rule. It's not like a super good argument, but it kind of works. And then when it's discharging, the capacitor the capacitor is in charge. The capacitor is driving the current. And so then it acts like kind of like the battery, in that it's a positive voltage. It provides the energy for the charges going around. So that's like our general rule, that capacitor voltage change is negative in the direction of the current for charging and positive in the direction of the current for discharging. But more precisely, we can look at the difference in charges here. And just very simply, we're going from positive when we're going around in the direction of current. So our positive terminal of the battery is on the right, so we know the current is going to flow clockwise here, right? And so if we're going through the capacitor, we're going to go in the direction of current from positive charge to negative charge. So plus to minus means a voltage drop. So that's one way that might help you. But anyway, so in this case, we get minus Q over C. Right, so the more charge that's on the capacitor, the larger the voltage drop across it. And then again, we have minus IR for the resistor. And so what happens over time is as the charge builds up, so as Q increases, right, charge building up, Q is charge, so as charge on the capacitor, so as Q increases, C is just a constant. So this term, this minus Q over C term, increases. The voltage of the battery is not changing. Right, so epsilon is constant. This term is becoming bigger, so we're getting E minus a bigger and bigger number. And so this term, the minus IR term, has to shrink in order for this equation to still be true, right? If this term's growing, this one has to go down. And R is a constant, right? The resistance itself isn't going to change. So what changes, it's the current, right? As the capacitor charges up more and more, it's going to become harder to pump current through the circuit, and so the current, less current flows through. And it slows down to equilibrium when we reach zero current. So once Q increases so much that minus Q over C is equal and opposite to epsilon, we get epsilon minus Q over C is 0, so IR has to be 0. In other words, current goes down to 0. And so that's why these circuits eventually decay away. So if we track that throughout time, we first connect the capacitor with no charge on it, right? This is at time equals 0. Our delta VQ is 0 because Q is 0. There's no charge, and so we just have our normal circuit. This one, when you first connect it, behaves just like there's only a battery and a resistor. Then we let some time pass. Some charge is up on the capacitor, and now we have some voltage drop across the capacitor, but it's not at equilibrium yet. There's still some current. It's just smaller than it was originally. And now the capacitor is fully charged, and like I said before, epsilon minus Q over C is equal to 0, and so there's no current and no voltage drop across the resistor. You need current flowing through a resistor in order to have a voltage drop. That takes the electrons bumping around and giving their energy to the resistor in order to do that. And so this is our equilibrium state after many time constants have passed. Okay. I don't know. Did I just double these slides up? I think I did. Great. Okay, so now let's take a look at what's happening to some of these quantities and connect it to the graph of exponential behavior, right? So we know how exponentials work, and we know intuitively how capacitors are working, but what does that look like? What does the charge over time look like when we plot it out? Well, we know, before we even look at the actual shape of the curve, we've decided that the charge builds up on the capacitor, right? So Q is going to start at 0 and increase as the charge builds up to some maximum Q that we can solve for by when we have IR equals 0, and so we can solve for what that is. But so the most general thing we know about this is that going from point A, our starting point, where there is no charge, to point C, where the capacitor is full, we're going to grow, right? But then also, we know that over time, it becomes harder and harder to put charge onto the plate, right? And this is where a connection comes between the charge on the plate and current. If we know the current is going to go down, which we saw from our loop rule, right? If Q increases, I has to decrease. If I decreases, then Q is going to change less quickly. Because what is I but flow of charge per unit time? And Q is how much charge lands on this capacitor. So those two things are intricately related. The lower I is, the less charges per second are going to be building up on the capacitor, right? And so if my current is decreasing, then the rate at which Q is changing also decreases. And that's where we get this exponential behavior where the slope goes from steep to more and more shallow. As current, the rate at which Q changes decreases away to 0. Now, this isn't exactly the equation we worked with before, but that's why I wanted to introduce exponentials as just looking at the change in the slope. Here, Q isn't really decaying, right? Q is growing from 0 to Q naught, or like the maximum value, but the rate at which it's changing is decaying, and that's what we're looking at, the decay of the speed that the system is changing. And so that the form of the equation is very similar. It's just instead of having e to the negative t over tau, we have 1 minus e to the negative t over tau. And I won't go through all plugging it in, but it just gives you the same type of graph flipped around, where we start at 0 and then asymptotically approach some finite value. And so, yeah, labeling these points on here. Early on, no charge, steep change. Middle of the way through, after some time constant, Q has now, it's 1/3 away from our final behavior. So because of this new form, we get 1 minus 1 over e, so 2/3, but maybe it's easier to just think, again, a third away from equilibrium, roughly, but big change and then slowing down until we're nearly at equilibrium when the capacitor is filling up. So Q increases, but the rate of change of Q decreases, and that's what we mean by decay. So we looked at charge, and we talked about current, but let's actually plot out the current here. Now, initially, we have some finite current, right? When the capacitor had no charge on it, we just had epsilon minus IR, some value of current, and then as Q increased, that term, that capacitor term, that voltage drop across the capacitor went up, the voltage drop across the resistor goes down because the current decreases. And so we see that the current is going to exponentially decay away. And this time constant is the same as the one in the previous graph. So even though these two graphs are different and they have different units, this time constant, which is equal to 1 over RC, just 1 over whatever this resistance is times whatever this capacitance is the same for both. Again, because I and Q are intimately related. I is the slope of Q. And yeah, so that's exponential change for charging a capacitor. And again, here we have our more simple equation for like actual decay, like shrinking decay, where we just have I naught times e to the negative t over tau. And again, that y, like the y of t equals y naught e to the negative t over tau, the y is just what becomes whatever value we're trying to evaluate, whether it's I or Q, like I just showed. You could also do this for the voltage change, right? The voltage drop across the capacitor or the resistor. All of these things are related to another just by either like multiplication or addition or something. And so if one of them is changing exponentially, which we've shown it is, they all are, right? The current is decaying away exponentially, and the rate of change of the current is the charge, so the charge is also decaying away exponentially. The voltage drop across the capacitor is just charge divided by capacitance, a constant. So that's just the exact same, just divided by a constant. The value just changes a little bit. The voltage drop across the resistor is just epsilon minus the voltage drop across the capacitor, so exponential change minus or plus a constant. And so we get all of these behaviors evaluate, like anything that's changing with time in this circuit is doing so in an exponential decay form with the same e to the negative tau, e to the negative t over tau involved. Just the starting point and the setup of like 1 minus or just e to the negative t over tau is different. Last thing, the values, this I naught, these Q naught, whatever, that or delta V naught, any of these things, those you get, and I don't have examples of it in this lecture, but those you get from evaluating the loop rule at the extremes, right? Because these I naught, Q naught, those are what the decay is going toward. Either they're the equilibrium value or a starting value. So for Q naught, for instance, that's the maximum charge. That's, as we just saw, the charge that we're growing toward. We know that's the case when the circuit is at equilibrium, when the current is 0. And so to solve for Q naught, I just set I equal to 0, and then I get Q is equal to epsilon times C. Right? I just move this over here, multiply by C. Or if I wanted to find the initial current, right? We know my current starts at some maximum value when there's no charge on the capacitor. And so if I want the initial current, I plug in for when there's no charge on the capacitor. And I just get epsilon minus IR. And I can solve for my initial current like I always do. So those, like I naught, Q naught, delta V naught, those just come from loop rule applied at the extreme, whether the starting point or your equilibrium point. And I don't have like a perfect rule for when you should do the starting point or the ending point, but only one of them will work, right? Because if I wanted Q naught and I try to look for the starting point, well then I already know Q is 0 there, so I kind of just figured it out. Anyway, let's look at discharging a capacitor. So this is all. We have an empty capacitor, connect it to a battery, and it charges up until it reaches the voltage drop of the battery, but we can also discharge it. So we charge up a capacitor, remove it from the circuit. The charge has nowhere to go, so it stays charged up, right? Just excess positive, excess negative can't leave, right, because it's not connected to anything else. And then we connect it across a resistor. And now when we connect it, it works just like a battery. The reason being, now there's nothing to force these charges to stay on the plates that they are. And they don't want to be there. Remember, they're repelling each other constantly because there's a lot of like charge on each plate. And so they're going to repel and flow back to bring the charge on each plate back to zero. The positives are going to flow around and land on the negative. So now if we do that same analysis to figure out whether the voltage change across the capacitor is positive or negative, I know my current is going to flow. The positive charges want to leave and come back to negative. So I get a counterclockwise flow. And so in the direction of current, I go from minus to plus. So an increase. And that just like the capacitor is driving the current. It's working like a battery, except the voltage is decaying away. It's like a battery that's quickly running out of juice in this case, because as more and more charge leaves, it becomes less eager to do so, and so the behavior decays away. So at this point, time t equals 0, fully charged, we just have our maximum Q, we'll get our maximum current. Some later time t, some of the charge has left, and so Q is smaller. And since here the only two terms we have are Q over C minus IR, if Q goes down, I goes down, right? So the current shrinks. And then finally, once it's out of charge, Q goes to 0, so I goes to 0. And now we just have a bunch of metal with no net charge on it sitting there doing nothing. So discharging a capacitor, this plot is kind of cool here. It's just plotting, this is a voltage versus time graph, except on the same graph we have the change in voltage across the capacitor on top and the change in voltage across the resistor on the bottom. So in this case, we know the capacitor goes from some positive value down to 0, and if the voltage drop of the capacitor plus the voltage drop across the resistor has to sum to 0, then at all times the voltage drop across the resistor is just going to be negative, whatever we have across the capacitor, right? And so that we get these two mirror image curves of each other that grow towards 0 as the current fades away. All right, that's all I got for exponential change. So now we got vectors. I'm going to speed through this part a little bit because we've been talking about vectors for quite a long time and using them in a lot of different complicated ways. So vectors graphically, magnitude and direction. So our magnitude comes from the length of the arrow, and the direction comes from, the direction of the arrow. Graphically, we add them just by putting them tip to tail. And then once we've put them all tip to tail, we identify a start point and our end point and just connect them. And so our F net, the total force vector, or whatever vectors we're adding, really, in this way, the net is just going from the start to the finish. To subtract them, it's very similar. Well, really the same thing. Just imagine your subtraction is addition, and the negative of a vector is just that vector with the arrow on the other side, and then we can do our same tip to tail to find the net vector, which would just be going again from the start to the finish. Algebraically, to add them, to complement our graphical method, we break them into components. So every vector, if we put down a set of coordinates, we can identify its x component, which is just how far it goes in the x direction, and its y component, how far it goes in the y direction, and identify that one vector with two numbers. And we could do the same for two vectors, and so our F net can also be split into this x and y component, and each individual one is just the sum of the components of the two. So if I have F1 and F2, my F net components are just the x is F1x plus F2x, and the same for y. And the x and y components are completely independent. So when we do problems like this, often the first thing we'll do is break them into components, then treat those two problems like they're completely separate. Maybe sometimes we'll use the answer for one to plug in something in the other, but the equations work independently, and then only at the very end do we put them back together with the Pythagorean theorem and some trig to get a magnitude and direction again. Because the magnitude and direction way of expressing things is easy to talk about, but not very helpful algebraically. Okay, so how do we find these components given a magnitude and direction? Well, we use trig. Again, I would not memorize f of x, like the x component goes with cos and the y component goes with sine. Rather, depending on whatever angle you're given, the x component not even the x component, but depending on the angle you're given, one side is the adjacent side, and that's the one that's going to match with cosine, and one side is the opposite side, and that's the one that's going to match with sine. So in this case, yes, x goes with cosine, and y goes with sine, but let's say I gave you this angle. In this case, the adjacent side to the angle here is y, and the opposite side is x. So I'd have the reverse of the trig functions. So really I would strongly encourage you don't make that link in your head permanently. Going the other way around from components to magnitude and direction, we have our Pythagorean theorem and inverse tangent. Again, be careful about which angle you're describing. I guess you can't really go wrong. I could always do theta equals tan inverse fx over xy or fy over fx, but the angle that I express, I need to make clear. So this angle here, if I did y over x, would be north of east or above the positive x-axis or whatever. If it was this angle here, it would be east of north or clockwise from positive y or whatever to the right of the positive y-axis. There's a million ways to say it. And maybe you even just, if you really hate all that language, you can also just draw a graph and a line and indicate what angle you're talking about. But you need to communicate somehow. When you just give an amount of degrees, that's not quite a full answer. Okay, so I've been using forces in these last few slides. What is a force? It's a push or a pull, right? It's a vector quantity, so it has a magnitude and direction, and it changes the motion of objects, right? So it doesn't take a force to have motion. An object can have a constant velocity and be under the influence of no forces, but if there is a net force, then its motion or its momentum are going to change. And it's done by one thing onto another. So what is momentum? The thing that gets changed by force. It's the way we describe an object's motion. It comes from the mass and velocity. Well, mass times velocity. So it's in the same direction as the velocity, except the more mass something has, given the same speed, the more momentum. Smaller mass, less momentum. Just like if you throw a bowling ball to somebody, they'll feel that had more momentum than if you threw them a baseball with the same speed. And the way a force changes a momentum is by applying a net force over a change in time. So F net delta t equals our delta p vector. J is our impulse, so you might hear that language. This is just kind of like a mediator, just like a way to talk about what a force does to change motion, but I almost never write J net down because these two are really the important parts and tell us about how the system's behaving. It's important to note that delta p, and we came across this when we talked about force and acceleration too, delta p has nothing to do with, but is completely independent of p itself. You could have any momentum and apply any change in momentum to it. And add those two vectors, however. Just because I know what my delta p is, does not tell me that I know what the object's momentum is. It just tells me the change in that momentum. So more about a momentum. Like we said, an object can still be moving if F net is 0. It just means our delta p is 0. And we often work with systems of objects. So total momentum is just the sum of the momenta of the objects in the system. And conservation of momentum works not just for an individual object, which on an individual object scale would just be saying that its momentum won't change unless we act on it with a force. But with a system, it's saying that if there's no net force on the entire system, then the sum of all the momenta, the total change in the momenta, is 0. So delta p total for a system is 0, whereas if you do act on a net force to the system, no matter where in the system you apply it, if you apply a net force on any part of a system over an amount of time, you'll get a change in momentum for the whole system. So we often use momentum charts to break behavior like this down. So this is just a really simple case of a ball hitting another ball. The second ball has what looks like a larger mass, and then once the first ball hits the second one, it comes to a stop, and so the other one shoots off. So identifying this in a momentum chart, we see ball 1 has some momentum, ball 2 has none, and so our total is just whatever ball 1 had. If there's no net force, then the total momentum in the system does not change. So the total momentum after the collision is still whatever that initial ball 1 had, except now it's spread out differently. Now we know that ball 1 comes to a stop, so its P final is 0. And so what that tells us is that whatever momentum ball 2 has at the end has to be equal to whatever the momentum that ball 1 started with. Ball 1 gave all of its momentum to ball 2, and so the momentum in the system is conserved. And the delta P column, which is interesting and that we studied more when we talked about Newton's laws, shows us that the delta P's for the individual objects were equal and opposite. And we could see that two ways. One, just by saying that the total change has to be equal to 0, so the sum of the individuals has to go to 0. So they have to be equal and opposite, but also we can find that from doing the math along the rows. And so that brings us to like the real key of momentum charts, is that they're just visual representations of a bunch of equations. Going down each column or across each row is an addition problem. P initial plus delta P equals P final going across, or momentum of object 1 plus momentum of object 2, maybe plus 3, plus 4, whatever, equals the total. And so filling these in strategically can help us identify where we're missing pieces of equations, and also where we can use information we're given in the problem to help work things out. And so the starting points for these momentum charts are always, well, obviously, what does the problem tell you? Like whenever you know the velocity of an object, you know something about its momentum. Also, this box right here, the total delta P, is often a gimme. If there's a net force, this is equal to that net force times delta T, or if there's no net force, it's equal to 0. Another quick tip from this is if objects stick together, we know that their final velocities have to be equal. So their momentum arrows might be different lengths because they might have different masses, but if they're stuck together, they have to be moving in the same direction. And so the total is also going to be in that direction. So that's a little key that helps us solve a lot of problems. Okay, so this is kind of just a more review of these things. I won't spend time on this, but just emphasizing that velocity is a change in distance over time. Kind of add-on topic for this is elastic versus inelastic collisions. Inelastic is when the kinetic energy is not conserved, and elastic collisions are when it is conserved. So to find the kinetic energy of a system, we just find the kinetic energy of each object, 1/2 mv squared, and add them up. So I do that for all the initial velocities, and do that for all the final velocities, and if they're equal, elastic. If they're not equal, inelastic. A key here, which we hopefully learned from the quiz, was that to find the kinetic energy of an object, you need the speed. You can't do that component by component. So v, like the magnitude of v squared. So like speed, let me just write this on the board so we can all see it. In the kinetic energy equation, what we have, it's not usually written with absolute values, but this is just emphasizing that it's the magnitude of the velocity squared. So if I have my velocity in terms of an x component and a y component, this is my vector v, then to find the magnitude squared, I can't do vx squared and vy squared separately. I need to find the magnitude of v first with the Pythagorean theorem. I need to do vx squared plus vy squared, take the square root of that, and then plug that in to the kinetic energy. So that's very important, because kinetic energy doesn't care what direction or whatever the object's moving. It's just how much distance is it covering per unit time. And so that's a small but very important detail in solving these problems. Another just quick, you can always test the numbers and see if it works, but if objects stick together, you know it's going to be perfectly inelastic. In other words, it's going to lose the maximum amount of kinetic energy. This is independent but complementary to conservation of momentum. So kinetic energy is not always conserved, and this is, you can have, momentum is always conserved, but kinetic energy is not always conserved, and knowing one does not tell you anything about the other. But you might be able to use one, like either conservation of kinetic energy if you know something about that, or conservation of momentum if you know something about that, to help solve things. Like if your missing variable is velocity or something, then they can be related, but you can have a combination of either or. So now let's start spinning stuff. Angular momentum and torques follow a very similar framework that we introduced for linear momentum, so just going in straight lines with two components. Now velocity turns into angular velocity. Instead of distance per unit time, we have angle per unit time. So how much angle did we subtend? Like 1 revolution, 2 revolutions, except we don't measure it in revolutions, we measure it in radians. And why? Because it's I don't know if it's technically a natural unit, but radians work out so that it's not really a unit. We don't need to cancel out radians and work with them. If I say like 1 revolution is 2 pi and give my angular velocity in radians per second, then I can plug it in and find other physical quantities without converting from degrees or whatever. So when you're doing angular momentum problems, set your calculator to radians. And if you can't or you're having problems with that, just keep it in like an expanded form and don't simplify, just so we know that you know what units you're working with. So I'll talk about the directions in a second, but coupled with angular velocity, we have angular momentum. And that, just like linear momentum, is not just dependent on what that velocity is, how fast is it rotating, but this rotational mass, which we call rotational inertia, or moment of inertia, I. And we have an equation for that, which I'll go over soon, but it just tells us kind of the equivalent thing. Like, we know that a carousel rotating around is going to have more rotational inertia than like spinning a pen on your finger. Right? It has to do with not only how much mass, but the arrangement of that mass. And as we'll find out, the further away from the center of rotation that mass is, the higher the rotational inertia is. But for angular momentum's sake, the faster it's rotating, the higher the angular momentum, and the higher the rotational mass, or the rotational inertia, the higher the angular momentum. So again, very similar to linear stuff. And then our equivalent for forces and changes in momentum are torques and changes in angular momentum. So I apply a torque over some time. Again, the more time I apply it for, the more angular impulse or more change in angular momentum I'm going to get. And so I get this nice, neat expression. And we know torque comes from force times r perpendicular, or force perpendicular times r, which I'll go over in a sec. The directions on that last slide, which I didn't talk about, are all determined with our right-hand rule. So if you're not solid on the right-hand rule, now's a great time to become so. We take our right hand, so like take your left hand, wrap it around your leg, sit on it, whatever. Get it out of the picture, and then wrap your fingers with the rotation. So sometimes that can be difficult, depending on the perspective, or if it's a static problem and nothing's actually moving. So you have to ask yourself, what direction does this torque want the thing to rotate? But we wrap our fingers with the direction of rotation, and then our thumb gives us the direction. So in this case, if this disk is rotating as shown, then we wrap our fingers like that, and we find that the angular momentum, angular velocity, everything points up. If something was rotating in the plane of the screen, and it was rotating from our perspective, so now I'm facing the board, if it was rotating from this perspective counterclockwise, we could wrap our fingers counterclockwise, and we'd find out of the page. Right? So you should get used to doing that. Yep.
Which ones are positive and negative again?
So positive and negative with these, we don't really need to worry about it, because we only need to know that they're opposites of each other. So in this case, if we looked at things that are like kind of in this flat plane here, we would just have up and down. And so if we were doing torque balancing, we would just want the ups cancel out the downs. It doesn't matter what's positive or negative. And if we were doing like an angular momentum problem where things are exchanging angular momentum, again, you just need to do one minus the other. It doesn't matter what the sign of that is, just really the change. So it's up to you. Is there any other question about that? Okay. So angular velocity, went over this. I'm going to skip through that. Rotational inertia. So the equation for it is the sum of mr squared for each mass element. So you'll only have to use this for simple cases where there is a finite, just 1 point mass, 1 point mass, 1 point mass. And what we care about is the distance from the axis of rotation. More specifically, like the perpendicular distance from the axis of rotation. So yeah, however far away it is times the mass of that point is the rotational inertia. If you're given an extended object, you'll just be given the rotational inertia. But remember, it depends on the axis of rotation that I choose. So I think I did this example in lecture, but if I spin this chair about the center that it wants to spin, it's going to have some value of rotational inertia, which we don't know what it is. It's some complex thing because this is a really weird shape, but it's whatever value, and it's pretty easy to spin. But let's say I picked my axis of rotation, instead of being the one that's going vertically right through the center, to be the one that's going horizontally right through the middle of the chair. Then the rotational inertia is going to express how hard it is for me to rotate the chair like this, end over end, which is much harder. And so I'll get a different rotational inertia. And in general, the more mass you have concentrated further away, the higher the rotational inertia will be. So we looked at like solid shapes versus hollow shapes. If you have two spheres and they're the same mass, one that's completely solid, so the mass is spread out through the whole volume, or one where all the mass is just in a shell and it's hollow, the shell one is going to have a much higher rotational inertia because all of the mass is concentrated at the outside. All of these individual mass elements, like the atoms in the ball, are going to have larger R values, whereas when the mass is spread throughout, some of it will be at the outside, but some of it will also be much closer to the center with a smaller R, and so have a smaller contribution to the rotational inertia. So that's something that you don't have to be super quantitative about when you have extended shapes, but it's good to just kind of review those, like the sheets I gave you, and just kind of try to work out with yourself why certain shapes or certain arrangements have higher rotational inertia than others, just to kind of get a feel for how that works. Okay, so torques. They come from forces, and not just forces, but forces applied with a specific orientation and distance away. So we care about a force, we care about the R, the distance from the axis of rotation, and we care about the angle between the force and that vector that points from the center to the axis of rotation. So on the left here, we have a force that is a distance r away from the center that's pushing on the edge of this, and it's at a 90-degree angle to this r vector. So it's completely perpendicular, which maximizes the amount of torque that this force can produce. Right? Any force that's perpendicular to that r is going to help with the torque, and any that's parallel to it will not. So like in this case on the right, we have a force that is still a distance r away. It's acting on the edge of this circle, but since it's completely parallel to its position vector, it's not going to cause any rotation. In other words, it's not going to cause a change in angular momentum. And in this case, it's pretty intuitive, right? If you pull on a bike tire outward, it's not going to spin, but if you push tangentially on it, then you will get it to spin. So they're not always set up so perfectly as we saw before. Most times you'll see a force that's at an angle to the r vector, and so we have to split it into components. Now we don't care so much about x and y, like horizontal and vertical. What we do care about are the axes with respect to r. So one axis we can define as parallel to r, and one axis we can define as perpendicular. In this case, they are just horizontal and vertical, but they don't have to be. And so we only care about that perpendicular piece. So in this case, it's f sine theta would be f perpendicular. I wrote f cos theta here, so that's just a typo. But let's say I gave you the complement. Let's say I gave you like another theta that was the angle between f and the vertical, then it would be cos. So this is just another example where you can't memorize like sine goes with x, cos goes with y, whatever. You just have to know what angle am I given, and do I want the adjacent or opposite side of this triangle. Sometimes we don't want to break our force into components because it's already nice and pointing in the y or the x only, and I don't want to make it some weird angle. Instead, we can break r into a horizontal and perpendicular component to f. So now we're making f our reference, and instead just finding the piece of r that's perpendicular to it. And it turns out that both of these approaches will give the same answer. This is different than the setup I showed on the previous slide, so they're not completely comparable. But in either case, I could have found the r perpendicular times f, or the f perpendicular times r, and both of those expressions are just going to give you f times r times the same trig function. The trigonometry works out, so that's always true. So either f perpendicular r or fr perpendicular, and those are both the same thing. So this is just a summary. So any questions on rotational stuff? Yeah.
Can you like draw an example where like R and F are like in weird like directions?
Yeah, sure. So the question was kind of like, let's draw, what if neither R or F is at a convenient angle? In other words, neither of them is perfectly vertical or horizontal. Let's just take a case where R points like diagonally down like that. So this is my R. And then my F points something like this, like also diagonally there. Now, neither of these are particularly pretty. So first I'm just going to say I'm going to look for F perpendicular. I'm going to say I'm not going to touch R and just go for F perpendicular. And sorry, can the people over here see this at all? This side? Okay, cool. So if I'm going to use, and this is a strategy that I like to use, I'm going to use R as my reference. So I'm going to draw axes that correspond to R. So one of those axes, I'll just draw with a dotted line, is directly along and going through R. So anything parallel to this is going to be the parallel component, which I don't care about. And then I'll draw another axis that's perpendicular to it. So this is the first step I like to do. Pick my reference, so in this case R, and then define these axes. And now I have a clear set of axes to break F down into. I have one component that's along the perpendicular axis, right? So this here is F perpendicular. That's what I care about to get FR perpendicular. And then this here would be F parallel. That's going parallel to R, but I don't care about that. I could have, instead of doing that, so keep F, sorry. So same exact setup. Let's say I want to use F as my reference and instead break R into an R perpendicular and R parallel. Now I'll just follow the same set of steps, except I'm going to use F as my reference. So I draw one axis that's parallel to F, one axis that's perpendicular to F, and now break R into those two. So now I have one component of R that's parallel and one component of R that's perpendicular. And I care about this R perpendicular. And I didn't label the angles here, but we would have seen that whatever angle I used to get F perpendicular, both of these would give me the same like FR sine theta, with the same theta everything. Maybe it's sine, maybe it's cos, whatever. But they would work out the exact same. And you could do that even if like F is already in the y direction. You could choose to make it harder on yourself and still use R as your reference and break F into two components. You're still just finding the perpendicular and parallel components. It's just kind of a way to make it a little easier to see. Okay, Newton's laws. Now we're getting into the home stretch. First and second law, we already knew them, right? First law is just if I don't apply a force to an object, its motion is not going to change. The second law is just re-expressing that delta P equals F net delta T. It's just now we're splitting delta P into m delta V, divide by delta T. Maybe you're following this in your head, maybe not, but it's the same equation. It's just it's expressly saying that our change in velocity over change in time is equal to acceleration. And that's just the definition of acceleration, the rate of change of velocity. So the second law is really just expressing that a force causes a change in an object's motion. And then our third law, this one we also kind of found out with objects that are colliding that experience this equal and opposite momentum change. But whenever you have a force on one thing by another, so force on A by B, there is always a corresponding equal and opposite force on B by A. So this one can lead to a lot of kind of mental tricks when you look at problems. But the key is that these two forces shown on this slide, F on A and F on B, are on two different objects. So there's no paradox here with like that problem with like the horse pulling a cart, and if the cart's pulling on the horse just as hard as the horse is pulling on the cart, how does it move at all? That's true. They are pulling on each other equally as hard, but those two forces are on different things, right? One's a force on the cart, and one's a force on the horse. So they don't add together to give a net force. We end up, if we look just at the horse, then we'll get the force on the horse by the cart, gravity, normal force, whatever, but then there's also the force on the horse by the ground from its hooves, and that cancels out the pull from the cart. So anyway, that's a lot of detail about this problem that I don't have in front of me, but this is always true, but it's important to remember that these forces are on different objects. And So when you're doing any problems, whether it's within the Newton's law stuff or kinematics or back into momentum transfer and looking at forces there, I really recommend you write forces out as on blank by blank. That's just another accounting thing that, yes, it adds a little bit of time to what you write out, but it really, really prevents a lot of mistakes. So yeah, that's important. If we look at a classic example, I just did this in lecture, but pushing a box, now we have, so there's, in the y direction, it's not interesting, or in other words, we'll apply the first law, so the first law is not very interesting, but I guess another thing to mention here is that all of these things, the Newton's laws were just about forces, right, and equalities between forces and acceleration, and they're vector equations, right? They're laws based on vectors, and so we still can apply that magical thing where we split them into components, they work separately. So any 2D equation, any 2D problem is just two 1D problems in disguise that we can take apart and then put together at the end. So taking this one apart, in the y direction, it's boring. It's just normal force and gravity that cancel out. And so if F net y is 0, that tells us that AY is 0. An object at rest stays at rest in the y direction. In the x direction, we have two forces. We have the force on the box by the person, the push, and the force on the box by the floor, which is friction. So that these are like a pushing force and friction, but us labeling them as on the box lets us know that these are all forces that we're going to put together and sum up because they're on the same object. So the net force in the x direction is just the difference between those two forces in the x direction, and the resulting acceleration is equal to, well, the force is equal to the mass times the resulting acceleration. So if we knew the net force and the mass, we could solve for how much the box is going to accelerate. This is another thing I just went over in lecture, but these relationships, like Newton's laws, yeah, they're not super different than what we did before. What is different is talking about acceleration and the relationship between that and velocity, and the relationship between velocity and position. And what this really is math. There's not much more physics that you didn't know. It's just using the math in a clever way. It's calculus and it's algebra, but the key kinematics equations are these two here, that your change in velocity, or your final velocity equation, and your change in position equation. So I'm not going to talk too much about plugging these in now. I think that would be more fruitful for like when I'm working on the board. But what I will talk a little bit about is the plotting, which I think that's something to really focus on the final. The kinematics problem that you get will be graphing focused. So you might have to do some kinematics work. Like, I'm not saying you won't have to do any equations or numbers, but what I really want to test is what we want to work on is more the plotting stuff, the conceptual part of it. I'm not going to give you a quadratic equation to solve, at least one that can't just be canceled out really quickly. So don't worry too much about that stuff, but have some practice. Anyway, in this case, we have a ball that's falling that has some x component of velocity. So like say I just threw a ball down and to the right, like is shown here. X direction, it's not super interesting, right? There's no net force. The only force here is due to gravity, which points straight down. So in the x direction, we can use our first law if we want to make it explicit, where no force, so no acceleration. And so whatever velocity we had is constant, which isn't shown right here, but we have a constant velocity. What is interesting is the y direction. So here we have some initial downward y velocity, and then in addition to that, we have gravity that's providing a force that's downward. And so we have a changing velocity that is downward. So if your acceleration is your change in velocity over change in time. In other words, it's the slope. So if I have a negative acceleration, which I do, the acceleration is negative g due to gravity, that means the slope of my velocity graph is negative g. So here, my acceleration plotted out, it's pretty boring, it's just negative, the number's not labeled, but it's just some negative constant value, negative g, and that means the slope, the rise over run of the velocity graph right above it is exactly equal to a of y. So if I just took 2 points on that velocity graph and found the change in velocity or the vertical change and divided it by the amount of change of time between those two, no matter what 2 points I picked, I would get negative 10 meters per second squared, or negative g, because that's what the acceleration is equal to. The only other important thing about the velocity graph is where it intersects the y-axis, so its starting point, and that just comes whatever my initial velocity was. So at t equals 0, before gravity starts pulling on it, how fast was it moving? And so that would, I guess, just be a given in this problem. Or maybe we could use trig to find it from v naught. But from once we get that initial starting vy naught, what you see in this kinematic equation for vy, this is just the equation of a line. We get a starting value plus an acceleration times however much time passes, which gives us a line. For the position, we get a parabola of some sorts. So this kinematics equation, the yf equals y naught plus vy naught t plus 1/2 ay t squared, that's just the equation of a parabola with t as your independent variable and y or x. These equations are the same, just changing y and x as your dependent variable. And so the things that change, your starting height, your starting velocity, and your acceleration, those just determine whether your parabola is facing up or down, and where you center it, and what the stretch of it is. But all of it is going to be this parabola. So in this case, if my starting height is 0, then my parabola starts at 0, and then my starting velocity is negative. So my initial slope is negative, and my acceleration is negative. So from that initial negative slope, my velocity becomes more and more negative, meaning my slope becomes more and more negative. So I start to curve downward. So it might be reminiscent of exponential change, but it's not exactly, because the slope doesn't asymptotically approach. Well, yeah, it doesn't asymptotically do anything. It just keeps evolving until it bumps into something, I guess. So in the x direction, I already went through this. I didn't realize I had the slide, but 0 acceleration, constant velocity. And so now our velocity versus time kinematics equation, this equation of a line, becomes very simple. It's just, this one becomes very simple because a is 0. So we just get v final equals v initial because there's no acceleration, no change in velocity. That's why our velocity is a straight line. And then our x equation, that simplifies from a parabola to a straight line because this 1/2 at squared term is 0, since a, acceleration, is 0, since there's no force in the horizontal direction. And so we just get x naught plus v, like initial speed times time. And so that's just a line pointing upward. Last piece here. Again, this is from a recent lecture, so I want to give time for a few questions at the end, but this is the same case as a block sliding on the ground. Y direction's boring, so we're not going to worry about that. That's 0 acceleration, 0 velocity, 0 position, all three of them. So that's not interesting. But here, we have all we know is that the acceleration is to the left because the net force is to the left. So that's why my acceleration versus time is a constant negative value, just in the negative x direction. But then, the way I draw my velocity versus time graph, all of them are the same, the line with the same slope, right? All three of these situations have the same slope, but depending on whether it was initially stopped, moving to the right, or positive x direction, or moving to the left, the negative x direction, it's anchored at different points. And this is just, so if it's at rest and has a negative acceleration, it will just start moving left and keep speeding up that way. If it's moving to the right at first, but its acceleration is to the left, that means over time, we're going to subtract away. So maybe it would be easier to talk about it in terms of positive and negative. Moving to the right means we have a positive velocity. So I have a positive velocity and a negative acceleration. That means my change in velocity over time is negative. In other words, over time, I'm subtracting away from my velocity. So from my positive velocity moving to the right, I subtract from that, meaning I slow down. Then I reach 0. But my acceleration is still negative, so now I start subtracting from 0, and I get a more and more negative velocity and start moving back to the left. If I'm initially moving to the left, then I'm already moving that way, and I just get faster and faster. So 3 very different scenarios, whether we're just moving to the left or moving to the right and stopping and turning around, all that comes from constant acceleration. And so it's very important not to automatically jump from acceleration to what the object's movement is going to look like, its position or its velocity. Acceleration just tells us the change. And so that change needs more to the story, which is where did I start? And then going from velocity to position, same type of thing where it's important where I start. All three of these graphs assume that we're starting at x equals 0, but since the first one, we're starting at 0 and moving left, we start with no slope, start with 0 velocity, and then gain a negative slope as we start moving to the left faster and faster. In the second one, since we have an initial velocity to the right, or in the positive direction, we start with a positive slope. So that's, even though this top line, the middle velocity graph, is pointing downward, the value of velocity is positive. Meaning, again, the slope of my x versus t is positive. It's just it's decreasing over time. So it's becoming less steep until it crosses 0. And right at the time when the velocity graph crosses 0 is when the x turns over, reaches a 0 slope, and turns negative, and then becomes more and more negative. And it will eventually cross this point it started. And then the third one, when it's moving left, it's it's very similar to the first one, except instead of starting with no slope, it already starts with some downward slope and just gets steeper from there. So there's a lot going on here. This is a great slide to study, and you can make slight changes to this all you want. Do y direction instead of x. Ask yourself, you can make up any situation where you have an object, pick an initial velocity, pick a net force, and then try to draw these graphs. And you should be able to do it. And you'll see where you need more information sometimes. Okay, so that's all the slides I have prepared. We still have 10 minutes left-ish for questions. Yeah. Oh, sure. Yeah, I forgot. I never went back to that. Thank you. So power dissipation. Right. I'm going to give people 1 sec just to filter out. And then okay, so for people that remained, and I appreciate you coming. I mean, I know you're doing this for you for studying, but this was really the only time that it made sense for me to have the review session. So good job for dedicating your part of your Friday evening for this. Power dissipation. So this is back when we're talking about circuits. We know that as charge travels through the circuit, the voltage tells us how much energy each one of those charges has. And we know when it goes through a resistor, it dissipates some of that energy, right? It loses it to thermal energy. And when it goes through the battery, it gains some of that energy. And so we have changing energy as a function of time at certain points in the circuit. And what energy divided by time is power. Sorry, energy over time is power. So looking at more like units-wise, again, we have an energy per charge, and we have a charge flowing through a circuit element per unit time. And so that gives us a power dissipation, meaning how much energy per unit time, a joules per second. So in a resistor, again, we dissipate it. Every coulomb of charge that goes through the resistor every second dissipates some amount of joules of charge. And when we go through the battery, every charge that passes through the battery every second gains some amount of energy. And so there is some energy flow into and out of the circuit. The power introduced or pumped into the circuit from the battery is just equal to the current times the voltage. So we can see that just kind of from units why that works out. Energy divided by charge, or energy density, is our current, is our voltage. Sorry, it's pretty late in the day. Energy over time is our voltage, and charge per unit time is a current. So these are the two values that make sense to associate with the battery. But the more charge that flows through the battery, so the larger the I, the more power is introduced to the circuit. So every charge that meets the battery gains some of that energy. And so the more charge, the faster the charge is flowing through, the larger the power. And of course, the larger the voltage of the battery, the stronger the battery, the more power it dumps into the circuit. And then a resistor dissipates power. So we don't have an epsilon for the resistor, we just have a voltage drop across the resistor. So the current times the voltage drop across the resistor is what gives us the power dissipation. So we can expand that a little bit. The voltage drop across the resistor is either equal to IR, well it is equal to IR, minus IR, but if we're just looking at the magnitude, we get I squared R. So this expression is a little less clear of why it is that. This is a current times a voltage, so that's why it's a power, but I squared R works well because we often know those two things. But it makes sense, right? The larger the resistance, the larger the power dissipation, and the larger the current, the larger the power dissipation. We could also plug in, we know that I equals delta V over R, so if we plug that in for this first piece, we get delta V squared over R. This one's harder to reason out why it goes up or down, but it works nonetheless. All three of these equations are exactly the same, right? We got them by just plugging things into each other. So it really just boils down to convenience. If I have current and resistance, I'll use the middle one. If I have voltage drop and resistance, I'll use the one on the right. But I could always quickly find the other thing. So if I was devoted, I always want to use I delta V for some reason, and I only have IR. Well, delta V is IR, so I'll just find out what that is and then plug it in here. There's no fundamental difference between any of these. It's just kind of plugging things in and turning it around. But power dissipation also has to obey conservation of energy, right? Whatever energy we dissipate in the circuit has to come from somewhere, and whatever energy we pump into the circuit has to go somewhere. So if I know how much power a battery is pumping into the circuit per unit time, that all has to be dissipated at the same rate by all the resistors or light bulbs or whatever in the circuit. And so if I find out my power introduced by the battery, that's going to equal the total power dissipated in the rest of the circuit. And likewise, if I find the total power dissipated by all the resistors, that tells me how much power is being dumped in by the battery. Another important thing about power is that it determines the brightness of light bulbs. So if you get a problem that asks, does the light bulb get brighter or dimmer or whatever, what it's really asking is how does the power dissipated in it change? Because lighting a light bulb is, expending energy over time. And so that tells, the power tells us how much energy per second is the light bulb dissipating. And so that if you want to compare, I guess you don't necessarily need to evaluate this for just does it get dimmer or brighter? But if you wanted to say something quantitative, how much brighter, how many times brighter does this light bulb get? Let's say I just have a battery hooked up to a light bulb. How much brighter does the light bulb get if I double the voltage drop across the light bulb? Right, so double the voltage of the battery, maybe that's simpler. Battery hooked up to a light bulb, the light bulb is a certain brightness. How does the brightness of the light bulb change if I double the voltage of the battery, right? So for that, I could do two things. One, look at my expression for power dissipated by the battery. If I double the epsilon of the battery, then that doubles, but current, we also have to factor that in, right? Because maybe my current will change. If I change the circuit by doubling the voltage of the battery, then my current's going to change. So both of these things are going to change. So I think the easiest one to answer this question in the fewest steps is actually to look at this equation here, my delta V squared over R. Because in this case, if I double the voltage of the battery, and I just have a battery and a light bulb, that means that I also have to double the voltage drop across the light bulb, right? If I go from 2 volts to 4 volts, then the voltage drop across the light bulb is going to go from -2 volts to -4. So this equation here just involves delta V and R. So changing epsilon doubling epsilon is going to double delta V, right? We decided that. And R doesn't change, right? Current will change, but the resistance of the light bulb, that's constant. You could do anything you want to the rest of the circuit. That's just a constant related to the characteristics of the light bulb. So if we double delta V, I get 2 delta V squared. And so I actually get a power dissipation that is 4 times what it was before. So the brightness is going to go up by a factor of 4 just by doubling the voltage of the battery. So that you don't need to memorize those numbers, but it's just to emphasize that power dissipation is important, that you can't just say like, oh, double the voltage drop, double the brightness. I need to evaluate the power dissipation equation. And then that was an example here where I saved some time by just using this one that only involved the things that I know. I could very easily have gone and said, okay, well, let me go to the board real quick. I have my loop rule. 0 equals epsilon minus IR, right? This is just voltage of the battery minus voltage drop across the light bulb. If I double epsilon, so if I plug in 2 epsilon, then, and I solve for my current, then I'm going to find that my current also has to double to 2I. So this maybe wasn't a great way to like, the way I'm doing the algebra, which is kind of not at all. But I hope you can see here that it's epsilon minus IR. If I double this term, I also have to double this term to keep this equation true. And so going back to the power dissipation equation, now I can use, if I want, maybe the power pumped in by the battery, double epsilon and double I. So that gives me power going up by a factor of 4, the same as I did before. Or now I could use the resistor one, where I, again, double I and delta V, but I just skipped a step before by only using what I know. But the most you could do, the most you could harm yourself is by adding one loop rule step, which isn't so bad. But yeah, any other questions? We have a couple minutes. Yeah.
Can we just go over how you define the different y-intercepts for position, velocity, and acceleration, and how they sort of relate?
Yeah. So y-intercepts for acceleration is just going to be whatever the acceleration is. So your acceleration versus time graph, if we have acceleration versus time, you're only going to have constant, or at least piecewise, meaning just like chunks of acceleration. So it's just like if acceleration is negative 10 meters per second squared, your y-intercept is that. For velocity, I guess it's kind of a given, or sometimes you might have to work backwards. But like let's say I knew before that I threw the ball down with a velocity of v naught, maybe like 30 degrees here. If I was working in the x direction, then my v naught x would be like v naught sine 30, and then so it just comes from looking at the problem. And same thing with the x. The x actually is maybe easier than the velocity, because for that one, it's just you get to define it. So if I have like a problem where I'm throwing a ball, I can define 0 to be the ground. I can define 0 to be 5 feet off the ground. I can do whatever I want. All that's doing is taking the same curve. So let's say the trajectory of the ball looks like that. It's just taking the same thing and moving my axes up and down. The shape of the curve stays the exact same. So the only thing that's really important when it comes to the y-intercept for position is that you keep it the same throughout the problem. But yeah, there's not too much to solving those, unless, of course, the problem is like, let's say you know everything else, what it was the initial velocity. In that case, you would just use the kinematics equations, where you might like, so if it asks for like the initial velocity and you know v final and acceleration, you would just plug them in and solve. But yeah, there's really no more tricks to it. All right, that's about all the time we have. Hope this was a good like Kickstarter to studying. And yeah, there's many, many more review sessions. Again, I'm having one next Friday for a last minute one, but I think most other people's review sessions tend to follow the more typical like question and answer practice problem style. So yeah, use as many of those as you want, and there will be Zoom ones. Yeah, the final is next Friday. My review session is probably the last one on Thursday afternoon. Yeah.